Hey guys, we're starting production and distribution of food. I'd like to call this the module where we see the main causes of all the environmental issues we've previously seen when we talked about pollution, degradation, soil, water, air, and deforestation as well. The next part of this module is going to talk about also the harnessing of energy, which is the other main cause of the environmental problems we're dealing with. So let's start with what we consider based on a 2200 calorie diet, a healthy diet. This is by the World Health Organization. The recommended would be including 7 grains, 3 cups of vegetable, 2 cups of fruit, 3 cups of milk, and meat and beans for 6 ounces. This is a daily value, right? So when we take a look at this, if we consider Panama, 6 ounces probably is not what we much more of animal protein and beans. Just looking at the average plate of food, only in one of our meals we are consuming more than those 6 ounces. And in terms of vegetables, yes, a lot of people consume these vegetables, but then again, if we're considering it locally, vegetables are very expensive. And as we know in Panama, there's a lot of inequality. Food is expensive, especially fruits and vegetables. So a lot of people don't have access to this healthy, recommended diet. So first, let's talk about production of food and the current situation. Obviously, through agriculture, more people are being fed with more nutritional food than before. In the last 30 years, food production has more than doubled. How has this happened? Well, changes in agriculture. We talked about first revolutions. We talked about the revolution, the Green Revolution, where we use pesticides and fertilizers. That's why we get more and less loss of food due to pests. We also have the fact that we're getting better at producing food. We talked about it with the environmentalist paradox, how we've enhanced, aquaculture, livestock, and crop production. And this is because we have developed high yielding crops or more biomass per hectare. Also, the trading of food. There's interchange of food between countries. Wherever something can't be produced, it's imported, and vice versa. And then genetically modified crops. So first we have to make the distinction between subsistence agriculture and industrialized agriculture. So we'll see one versus the other. Subsistence farmers have small parcels of land to provide food to their own household and produce small amounts to sell. So a couple of things. Worldwide, 500 million support more than 2 billion people nutritional needs this way with the subsistence agriculture. 80% of food consumed in Asia and the sub-Saharan Africa, subsistence agriculture. Sometimes changes to the land must be done, like clearing parts of tropical forest. It can work because of the small population and because trees come back as plantations, agroforestry. Okay? Very dependent on rainfall and pest control. People like this live on the edge, just waiting for the best conditions and also pest control. And then this is common in Asia, Latin America, and the sub-Saharan Africa. Now, industrialized agriculture is another story. Industrial Revolution transformed agriculture, increasing the effectiveness of farming. So you use machinery, use infrastructure, huge areas can be cultivated. So huge areas are deforested or like I said, other ecosystems can also be degraded or destroyed, like prairies, etc., to use for cultivation. So we lose a lot of biomass, a lot of species, and diversity when we have to clear all this land. Fertilizers and pesticides are used readily here. Fertilizers are more readily available than manure, so it increases the yields of crops. You can use large quantities of these synthetic fertilizers and um, use for crop production. Fertilizers use energy, fossil fuels, for their production. Therefore, um, they're going to have impacts. The price of fuel rises, then food cost is going to rise, right? When we talk about industrialized agriculture. And then pesticide control, the pest, but lots of pests have become resistant, okay? Especially because of this, because we have um, just in this kind of agriculture, we use so much pesticides that plants eventually deal with these pests that are resistant to the pesticide. So when we talked about water use, remember, and degradation, we talked about irrigation taking 70% of all the water used. So you're going to use a lot of water in these huge areas that you have to irrigate. There's going to be problems with diseases where there is bad drainage. So there's lots of water and there's not good drainage. You can get, for example, mold and fungus and other different things that can attack the soil and the vegetation and the crops. Okay, and then we are running out of water the way we're using it with this practice. A little more in the Green Revolution, we talk about increase of crop production. How? Yes, we do use the pesticides and the fertilizers, and also we have come up with new varieties that produce double and triple the yields. So in the same amount of land, you can get much more food. That's part of that, remember, environmentalist paradox, how we enhance food production is by just being able to yield more in the same area. So corn, wheat, and rice are perfect examples of how we manipulate and cross different varieties until we get that high yielding product. So modern agriculture, especially with the industrialized agriculture, is going to have its costs. So like I said, water shortages are impacting the high yielding crops that require lots of water. Monocultures, vast areas with just one crop, making pests and diseases spread more rapidly. I haven't talked a lot about this yet, but biodiversity is very important. So if you have biodiversity, you have competition, and you have certain areas where one plant can just help the other plant survive. So they kind of live in a environment where they live in a balanced environment, and pests are not going to attack just one culture, but many, and they kind of help to maintain the health of the environment. Perhaps if you have a plant that is next to another plant, and that other plant is being pollinated, or you know, some other animal feeds from this other plant next to your culture, and then that say animal that's consuming or pollinating that neighbor plant to your culture starts feeding also on the pest that's attacking your culture, then you have a healthier environment. The point is, you do need this biodiversity. You need this competition. Okay, so it's very important to understand it this way. Loss of genetic diversity. You have domesticated plants are developed and thousands of the original varieties are lost. So what are some solutions to this loss of genetic diversity? We have solutions that are seed banks. In this website, you can see a couple of these seed banks. They're the 15 largest seed banks in the world. And what they do is they usually freeze these seeds in case we need those varieties or we need those species again. We can go to that bank and we can again add this to the environment, add this to the ecosystem. Okay. So we get to animal farming and its consequences, it gets even worse. So we need to produce food. So now we're producing food for us. We were talking about crops for us, but when we want to farm animals, we need to also produce food for them so we can have that animal protein ultimately. Okay, so we're gonna require energy, we're gonna require water, space, okay, food for this farming. So concentrated livestock production have damaged the environment and human health. How come? Like I said, so add whatever the problems we have with agriculture to um, adding even more nutrients in the environment. We can cause eutrophication like we saw before. Diseases among animals that can spread to humans, like avian flu, salmonella. Now we see the COVID-19, okay, that the most accepted theory of how this started was from an animal to human, okay, so transferred. And then use of antibiotics. There's use of antibiotics when animals are all clumped together. So we need to use those antibiotics, and they could have an effect also in our health. Okay? And not only in our health, but it can also, those antibiotics can spread to the environment and have other consequences, end up in the waterways and wreaking havoc. So large ranches, taking massive lots of land where most every crop, trees, and natural environment is altered or destroyed by the activity. So for the most part, you're going to need grass or you're going to need certain kinds of crops. You're not going to have that natural vegetation, that native vegetation, so you're going to have to clear land for the environment is actually altered by this activity. See a couple more consequences. Climate change, release of more greenhouse gases and transportation, carbon dioxide, methane, and nitrous oxides. Does the animals themselves release methane, for example, and other gases? And also, you have to transport a lot of times, or most of the time you're going to transport these. You are going to also required to clear land, like I said, so you're going to lose all this carbon sequestration you had. Okay. An alternative, or better alternative, is pastoralist, which we're seeing more and more, which are farmers that move their grazing animals from place to place. So they're moving their cattle or whatever they have to different places to feed, and this is because they, let the specific field where they were feeding before to come back. So if you have all these animals, excreting their manure, their urine, and at the same time they are just feeding a lot from that area, you're going to have a eventual fast degradation of that area. But if you move your animals, you are going to mitigate the problem. Okay, their manure helps as fertilizer and helps poor families. So manure is actually used, but if you move the cattle around, it's not going to be excess of this excretion, and you are actually going to help the environment. So it has time to be resilient. Okay, for these questions, you are going to have to read an article that I am going to post right on the module, right under module 3. So please read that short article, it's just 1 page, and then answer these 4 questions that I have here, and then answer the questions that are on the bottom of the article. So with genetically modified food, we apply genetic engineering, which is the incorporation of desired traits from different organisms that can be obtained, also called transgenics. This is exchange of genes among bacteria, animals, and plants. Example is making a tolerant to herbicides and resistant to pest crop. Okay? Traits that we want, and then we kind of play with the genes. The downside of genetically modified food would be proteins from different organisms may pose a threat to consumers. Okay? Development of super weeds and resistant pests, and then loss of biodiversity can outcompete the native counterpart or hybridize. So it can outcompete some of the other, vegetation around the area. So sometimes a product might not be, marketed as a genetically modified food, but some of the ingredients may contain already genetically modified um, processes. So it's estimated that 70% of all processed food in the U.S., for example, contains some kind of GMO. With the Cartagena Protocol, this stated that the right for countries to deny the entry of GM food. So food must be labeled saying if it's genetically modified, okay, and then just have the right of deciding once you're informed and you know if that's a genetically modified food, if you're gonna let it enter the country. This happened with the Cartagena Protocol. So food is produced and distributed. So now we go to the distribution. So after the Industrial Revolution, and especially with refrigeration and faster shipping, food could be conserved and transported and traded around the world. So in 2013, world trade in agricultural products was worth $1.75 trillion. Agricultural production is more than what the internal demand of food is, so cheaper to import and helps the exporter. In the case of, say, the developed countries importing their food, so it's cheaper to buy sometimes from other areas, also less costly to their environment or their ecosystem because food doesn't have to be produced there. Okay, it's somebody else's environmental problem, and then a lot of times, like I've said, it's bought or traded to developing countries. So these developing countries get helped by what the developed countries buy it for. Okay, so in certain cases, it helps the exporter. It is damaging to the environment in different ways. You have to think of the transportation. So in transportation, we already have, release of pollution, overexploitation of natural resources that an area may sustain. So you are not consuming what's local. So you're already posing a problem to the environment with the transportation, but also with overexploitation to other areas, just degrading somebody else's soil, somebody else's water, and somebody else's atmosphere, air. Okay. So even though we are feeding more people and we have managed to even improve the nutritional value of the food and give better nutrition because we know more about nutrition and better at transporting, producing, etc. There is increasing population, so we do still have a food crisis. There's depletion of natural resources. So again, with the limiting factor, the law of limiting factor, remember, areas that are good for crops are not available anymore because of all this degradation that we've caused. Water, the crisis with water, and yeah, it is becoming a problem. Degradation of the environment, like I said, farmers in high-income countries dominate food export. On the other hand, farmers in developing countries get paid less. So in developing countries, they may have to import food and get faced with prices they can't afford. Food expenses can be more than half their income, and food prices increase where it can lead to hunger and malnutrition. So at the beginning, I added this chart with the recommended um, amount of calories and in what proportions of different food groups should be consumed daily. That was with the purpose of showing you what we have as for food consumption and food availability. So the sum of all the food divided by the world human population gives us 2,700 calorie per day diet. So if you take all the food that's produced and we add it and divide it by the amount of population, we would have 2,700 calories per day. The recommended was 2,200. So we have more than the recommended value for everyone. The thing is, 1 billion people suffer from hunger, while at the same time, 500 million people are overweight. Okay, so there is definitely just a bad distribution of food. Why? Politics and economy, bad management. More than half of the crops are utilized to feed pigs, cows, and other livestock. And as you saw in that article that I shared before, what are the ones that have the highest impact? Um, you saw that we had beef being the highest one, or the one that taking the highest toll in the environment. So we focused a lot on terrestrial environments, all the problems that we have with agriculture, deforestation for urbanization, soil degradation due to um, the agriculture, livestock, etc. But we haven't talked about the oceans, and yes, oceans are very important. First of all, in the carbon sequestration, about 30% of all the carbon is sunk into the oceanic environment. Um, Another 45 is still in the atmosphere, and then the rest would be in the terrestrial um, areas, right, where we get most of our food, our vegetables, etc. But in the oceans, where we do have a big pollution problem from um, debris and contaminants that come from rivers and end up in the ocean, from direct introduction into the ocean, we have a massive problem with plastics, with organic substances, inorganic substances, heavy metals. We find all kinds of contaminants there. Yes, so we do have a problem, and we will talk a little bit about it in this section of food production. Okay, and let's take a look at it. So, if we were to eat mostly from the marine environment, we could say that it is a pretty renewable source. Okay? Fish have high fecundity and their population is resilient. 1 billion people depend on this resource as their main protein source. Say about 14% of people rely on oceans for their animal protein. So it's a pretty big chunk. This food contains high concentrations of omega-3s, making it the healthiest animal protein available. Marine and freshwater products would be the best solution for a sustainable, plentiful, and healthy diet for the planet, if managed well, if taken care of, if it wasn't that polluted. Okay? So if done right, we could say this is a pretty renewable source of food or natural resource for our animal protein, which, by the way, is the one that takes the highest toll when we talk about animal protein taken in terrestrial environments, right? So it seems like fish and seafood are a great option for our health and our environment. So what is the downside? So, like I said, we're not taking care of our oceans. There's a lot of contamination. Some fishing techniques currently used can be detrimental. For example, bottom trawling and trawling, which is picking up everything in the path and disturbing the benthos or the bottom of the ocean, the bottom, the substrate, and the marine environments. such as corals, very important um, areas. Bycatch and fishing discards. About 40% of all fishing occurs with bycatch. Okay, so we get everything that's in the path and then we just discard, and it's either dead or not utilized. So terribly, terribly degrading and bad. In certain areas, there's still the use of cyanide for fishing and dynamite explosives. Okay. And then ghost nets and cages, just nets that are, or cages that have been lost at sea or just left there, can also be a menace to marine life. This is the bycatch I'm talking about. You can see um, probably aiming for, I'm not sure what they're aiming here for, but if they were aiming for sardines, then they get all these crabs and starfish, and then these are discarded and probably not alive. So we lose a lot of organisms and even species. This is just an example of trawling. So this trawling takes most everything in its path. Now there's nets that are safe or safer, so they will exclude a lot of organisms that would otherwise be taken in nets that are not safe. So they have gotten better at trawling, but this was a big problem, and it's still a big problem in many areas. I have other issues with the way we are capturing and gathering this natural resource in the oceans. Our preference for some fish over others. Okay, so tuna, salmon, which are bigger fish, and also wanting imported fish. So we have to deal with transportation, in which we talked about pollution in that sense. Um, and yeah, tuna and salmon, which are highly in high demand, and they're not the most easily reproduced or the fastest reproducing with high fecundity, like for example, smaller fish. So that's also a problem. Our choice, the what we're choosing for that animal protein. As for aquaculture, I have here a solution or yet another problem. Well, 50% of the fish and seafood that we eat comes from this industry. Okay? So it wouldn't be going out there, but actually culturing it in pools, tanks, and sometimes in coastal areas. So, yes, it is a big source, but we'll present a couple of cases here so you can know what happened. So, the case of salmon. Salmon had been effectively raised with this method, but the meat of these individuals have half the amount of omega-3. So, okay, we lose some of the health properties that it has. And then it's still a much better choice than red meat, for example, for our health and the environment. But we are losing some of it over the one that we would find wild caught, right? So Chile Salmon's farm case, these guys were kept in corrals, first run in pools, then kept in corrals. So there was high demand for this fish. There is high demand for this fish. This high demand had the industry concentrating too many individuals in one area. What happens when you do this? You're going to have animals eating and excreting in the same area. So this is not an ideal situation for sure. Not for the animals in the farm, but also the water around it and all the other flora and fauna around it. So food and waste produced along with the antibiotic application, because they had to add antibiotics because of what I said, the problem with eating and excreting in the same area, polluted the water, affecting all the surrounding environment and even the fish that's not healthy. Okay, so this industry with sound practices has helped with the supply of food for sure, but it's not the solution to the animal protein demand. There's still a lot of overexploitation in marine and freshwater systems. Even though we have this agriculture, there's a lot of, demand for wild caught, for species that are more concerned because we have been depleting them for years, and then not the ones that I said that are more renewable. because of their fecundity and reproductivity. So uh, resources are needed to feed and maintain this industry as well. So we also have to feed these guys, as we have to make space and food for terrestrial animals. We also have to, um, you know, feed these guys. So the pellets or food given to aquacultured fish is usually pellets made from anchovies, sardines, and herring. So the anchovies are perfectly abundant, delicious fish, and it's not the favorite among humans, but it's definitely a one of those fish I was talking about with high fecundity, easily reproduce. You have huge biomass, massive amounts of fish that come out of these breeds. So this is a protein to consider for sure, okay, and to choose and try to get used to. I remember when I talk about what are you willing to give um, to not reach that carrying capacity. Well, these are small changes that we could have in the way we eat and the choices we make. Here are just some of the solutions. The other cause of um, environmental issues that we've been studying, harnessing energy for human use. It's a graphical representation of the um, global primary energy supply with oil being at the top, fossil fuels 32.9%, then followed by coal 30.1%, and then natural gas, and then the rest. We could talk about our the renewable resources, and then better alternatives like nuclear power and hydropower. Some facts on our use of um, sources for energy worldwide. 87% come from crude oil, coal, and natural gas. Okay. Um, by 1951, crude oil became the leading energy source in the US, now the most widely used, 32.9%, as you saw. Coal, following it at 30.1, still the dominant source in China and Eastern Europe, and is the dirtiest of them all. Natural gas comes in third place, 23.7%. Largely methane, usually found in the surge for crude oil, only releases carbon dioxide in water as it combusts. Therefore, it's cleaner than coal or oil for heating, cooking, industrial process, but still, like I said, is usually found when you are looking for crude oil, and that has its terrible environmental impact. And then the rest relies on hydropower, nuclear power, and renewable resources. Just here a graphic showing the formation of fossil fuels. It will take thousands to millions of years to form, therefore not renewable at the rate that we use it. So we take these natural resources and we do electricity, which is an energy carrier. It transfers energy from primary source to its point of use through generators, turbine, gas, steam, or water, turbo generators. Just a question if electrical power is a clean energy. Well, using it creates no pollution, but generating it does. Obviously, to acquire the sources will take a toll on the environment. So it is dirty. It is pollution cost. So it is also expensive due to its generation from fossil fuel and nuclear energy. Some facts on crude oil. The price fluctuates, as you can observe, um, you know, daily, weekly, with the gas we pump into our cars. Um, causes trade imbalances, economic disruption, and even oil spills. So I said natural gas is usually found in the search for crude oil. So there's shale and gas fracking. Natural gas is found around shale rock formations, and these are tapped by conventional vertical wells. Um, but then there's also fracking, or hydraulic fracturing, was using hydraulic fluid containing sand forced into the pipe by huge pumps, fracturing the shale and releasing gas into space. This has made shale source rise 20%. So it is a more effective, faster way of getting the natural gas, but at the same time, it's highly disruptive. It contaminates, pollutes water, air, and it has health consequences, and it even creates earthquakes, local earthquakes. Like I said, mining coal is probably the dirtiest, not probably, it is the dirtiest resource that you can uh, get um, for energy generation and energy harnessing. World most abundant fossil fuel. It's 80% electricity in China, so still the biggest source in China. 45% electricity in the US. It's less expensive than natural gas and oil, but mining can be hazardous. There's explosions, black lung disease from people that work in the mines, surface mining or ground mining, which causes degradation of rivers and lakes with waste and product that leach from mine waste. So, what are the solutions to the energy production? Look for alternative energy sources, resources. Lower the rate of consumption as well. Okay, like I said when I talked about the carrying capacity, are we willing to stop using or lower our consumption of energy through ACs, um, through heating? What are we willing to do and adapt to, okay, to reduce that? Increasing the mileage standards for motor vehicles, increasing the energy efficiency of lighting appliances in buildings, encouraging industries to use combined heat and power technologies, promoting greater use of non-fossil fuel sources of energy, nuclear and renewable. So nuclear power, I'm not going to have it in the group of renewable energy, but it is almost renewable, saying that you can produce from very little, um, almost infinite amount of nuclear power. The pros are no carbon dioxide emission, no acid forming pollutants. The cons, accidents, radioactive emissions from accidents, or waste disposal or storage. Okay. Uranium is used to produce this reaction. For example, it's taken through mining. So mining is going to have an environmental impact. It's plentiful and it's highly efficient. So from very little, we can produce a lot of energy. So radioactive emissions can have all these problems. Biological effects at high doses prevent cell division, prevent normal replacement of blood, skin, and other tissues, thus killing organisms. So in low dose damages DNA, malignant tumors, damage DNA in eggs or sperm, and may cause birth defects. Exposure, people working in plants increase the risk of cancer, for example, exposure to x-rays. So these are bad things that can happen, for example, if we have an accident or if we are receiving it in low dose. Another problem with radioactive decay, unstable isotopes. Radioactive material becomes stable eventually, right? But radioactive material isolated from humans and environments goes through decay harmlessly. Nuclear waste, okay, or spent fuel, and water that has been used in the process as well has to be taken care of. That waste has to be taken care of in a way that it can be contained, depending on the life of those isotopes until they become stable. But then you have to make containments that can last from 10 years all the way to 10,000 years. So So those are very expensive, and nobody wants this their backyard, so to speak. So the geologic burial is another thing that we have to think about. All the waste that's produced from radioactive decay has to be taken care of, has to be placed somewhere safe, and the site has to be a site that has the perfect geologic conditions of the rock, and hopefully it doesn't have big earthquakes where these can come out at some point. So they are in special places of our planet, and then we have to find areas that will accept those wastes. So that is one of the biggest problems that we have with nuclear power. And then, of course, the accidents. These next slides, you will see a couple of the accidents that we've had. The 3 Mile Island. Okay. Next, Chernobyl in 1986. Okay. While they were conducting a test, the power plant was disabled, withdrew the control rod, shut off the flow of steam to the generators, and decreased the flow of coolant water in the reactor. So human error, they forgot to allow radioactive heat energy generated by the fuel core out, and the reactor began to heat up. They didn't have the coolant or the coolant water, so it blew 200-ton tough reactor, which melted down, and fire was ignited. 100 to 200 million curies reigned over thousands of square miles. 135,000 people had to be evacuated and relocated. 1,000 square mile exclusion zone around the reactor site, killing 2 engineers and 28 workers. But there has been reports of people that were in the periphery of the area that were all affected somehow with different diseases and problems after this accident. So it wasn't only those lives that were taken, but a lot of health issues after years after. Another accident was the Fukushima Daiichi. After an earthquake and tsunami, no electricity could provide power to the cooling reactors. There was no way to provide cooling, and therefore there was nuclear meltdown, hydrogen explosions, and the release of radioactive material. So this is what we want to look at and what we should be looking at. And this is renewable energy collected from renewable sources that can be replenished: sunlight, wind, rain, tides, waves, and geothermal heat, and produce the least possible pollution.
Hydropower. Hydropower, or hydroelectricity, refers to the conversion of energy from flowing water into electricity. It is considered a renewable energy source because the water cycle is constantly renewed by the sun. One of the first uses of hydroenergy was for mechanical milling, such as grinding grains. But today, modern hydro plants produce electricity using turbines and generators. The mechanical energy created by moving water spins rotors on a turbine. This turbine is connected to an electromagnetic generator, which produces electricity when the turbine spins. There are 2 main types of hydroelectricity production: dams and run-of-river. Hydro dams utilize the potential energy from dammed water to produce electricity. A dam is a large barrier constructed to raise the level of water and control its flow. The elevation created by the dam creates gravitational force for turning the turbine when water is released. Some dams also contain an additional reservoir at their base where water is stored to be pumped to the higher reservoir for release when electricity is in demand. This is referred to as pumped storage hydro. The second form of hydroelectricity production is run-of-river hydro. Run-of-river still uses turbines and generators, but relies on natural water flow rates of rivers, diverting just a portion of the water through turbines. Because run-of-river hydro is subject to natural water variability, it is more intermittent than dammed hydro. There are various sizes of hydro plants that produce electricity. Large hydro, greater than 30 megawatts, small hydro, 100 kilowatts to 30 megawatts, and micro hydro, less than 100 kilowatts. The Hoover Dam in the United States is a whopping 2,074 megawatts, which is enough to serve 1.3 million people. Of all renewable energy sources, hydropower holds the largest share of worldwide electricity production. Hydropower has several benefits. It is a cost-competitive form of electricity, even though the initial building cost can be high. It is quite reliable compared to other renewable options and pairs well with other sources as it can be used as base load power. In some cases, dammed reservoirs can also help with flood control and be a reliable water supply for communities. There are also some concerns with hydropower, especially when it comes to large dams. Damming a river has a major impact on the local environment, changing wildlife habitats, blocking fish passage, and often forcing people in riverside communities to move out of their homes. In addition, dam failures can be catastrophic, claiming the lives of those living downstream. Hydro plants are also not completely free of greenhouse gas emissions. As with most forms of energy, carbon dioxide emissions happen during construction, particularly due to the large quantities of cement used, and plant matter in the flooded areas makes methane, another greenhouse gas, as it decays underwater. That's hydropower.
Renewable Energy 101. We've been harnessing the wind since the ancient Egyptians used sailboats to travel, and windmills were used in agriculture in China over 2,000 years ago. Americans were using wind turbines to produce electricity as early as the 1800s. You may have seen fields of turbines in wide open spaces where you live, since more than 3/4 of US states produce wind energy on a large scale. They may look small from a distance, but a modern turbine can be as tall as a 20-story building, with airplane wing-shaped blades that are as long as a football field. The blades spin at a slow speed of about 1 revolution every 3 seconds. A computer inside the box that sits at the top of the tower controls the direction of the blades to make sure they capture the most wind possible. The blades are connected to faster spinning gears inside the box that create kinetic energy. A generator converts that energy into electricity, which travels down the tower through a cable. The cable connects to the power grid that serves our communities. See? All it takes is a little fresh air to make the turbines go round.
Biomass. Biomass energy, or bioenergy, refers to energy produced from organic matter. Biomass is primarily found in the form of living or recently living plants, as well as waste. The term feedstock is used to refer to whatever type of organic material will be used to produce energy. Different feedstocks will have different physical compositions, but generally all feedstocks include varying amounts of carbon, water, and organic volatiles. For energy production, a feedstock must be converted using one of many processes. Some common biomass conversion processes include combustion, the process where feedstock is burned in the presence of air to release heat, what happens when you start a small campfire with wood. Combustion can be used to heat steam for electricity generation as well. Gasification, the process of using heat, pressure, and partial combustion to convert feedstock into a combustible gas mixture called syngas. The syngas can then be used in place of natural gas for heating, electricity, and other uses. Pyrolysis, the process of heating feedstock at high temperatures in the absence of oxygen. Since no oxygen is present, the organic material does not combust. Instead, the chemical compounds decompose into 3 forms: a liquid called bio-oil, a solid called biochar, and a syngas, which we talked about earlier. Anaerobic digestion or biodigestion, a process where bacteria breaks down organic material in the absence of air to create biogas, which can be captured and burned to produce energy. The remaining byproduct is called digestate and makes a great fertilizer. Fermentation, the process of converting a plant's glucose into an alcohol called ethanol through the use of yeast. The ethanol is a liquid fuel that can be used as an automotive fuel. It is important to note that certain feedstocks are more conducive for some biomass conversion processes over others. The determination of which feedstock and process will be used is determined largely by the availability of resources and the desired end form of energy. Prior to the Industrial Revolution, biomass was the primary source of energy. Biomass now makes up only a small percentage of total world energy use. However, for approximately 2.5 billion people, it remains the primary source of energy for cooking and heating. The use of biomass is highly contextual to the region in which it is used. Availability of resources, availability of technology, and economic viability are all drivers of biomass use. The environmental benefits and costs are highly contextual depending on the technology and feedstocks used. While some biomass processes, such as waste to energy, are touted for their lower carbon dioxide emissions, some processes, such as combustion, release carbon dioxide and particulate matter that are a significant concern for human health. The world's most energy-poor peoples and regions still rely on biomass for the majority of their energy needs. The lack of appropriate ventilation mechanisms for burning biomass is a major health concern and contributes to short life expectancies in much of the developing world. Concerns associated with biomass also go beyond human health. Depending upon the source of biomass used, deforestation, cropland degradation, and land use alteration can all be relevant issues associated with biomass. That's biomass.
The Earth intercepts a lot of solar power, 173,000 terawatts. That's 10,000 times more power than the planet's population uses. So is it possible that one day the world could be completely reliant on solar energy? To answer that question, we first need to examine how solar panels convert solar energy to electrical energy. Solar panels are made up of smaller units called solar cells. The most common solar cells are made from silicon, a semiconductor that is the second most abundant element on Earth. In a solar cell, crystalline silicon is sandwiched between conductive layers. Each silicon atom is connected to its neighbors by 4 strong bonds, which keep the electrons in place so no current can flow. Here's the key. A silicon solar cell uses 2 different layers of silicon. An N-type silicon has extra electrons, and P-type silicon has extra spaces for electrons, called holes. Where the 2 types of silicon meet, electrons can wander across the p-n junction, leaving a positive charge on one side and creating negative charge on the other. You can think of light as the flow of tiny particles called photons shooting out from the sun. When one of these photons strikes the silicon cell with enough energy, it can knock an electron from its bond, leaving a hole. The negatively charged electron and location of the positively charged hole are now free to move around. But because of the electric field at the p-n junction, they'll only go one way. The electron is drawn to the n side, while the hole is drawn to the p side. The mobile electrons are collected by thin metal fingers at the top of the cell. From there, they flow through an external circuit, doing electrical work like powering a light bulb, before returning through the conductive aluminum sheet on the back. Each silicon cell only puts out half a volt, but you can string them together in modules to get more power. 12 photovoltaic cells are enough to charge a cell phone, while it takes many modules to power an entire house. Electrons are the only moving parts in a solar cell, and they all go back where they came from. There's nothing to get worn out or used up, so solar cells can last for decades. So what's stopping us from being completely reliant on solar power? There are political factors at play, not to mention businesses that lobby to maintain the status quo. But for now, let's focus on the physical and logistical challenges. And the most obvious of those is that solar energy is unevenly distributed across the planet. Some areas are sunnier than others. It's also inconsistent. Less solar energy is available on cloudy days or at night. So a total reliance would require efficient ways to get electricity from sunny spots to cloudy ones, and effective storage of energy. The efficiency of the cell itself is a challenge too. If sunlight is reflected instead of absorbed, or if dislodged electrons fall back into a hole before going through the circuit, that photon's energy is lost. The most efficient solar cell yet still only converts 46% of the available sunlight to electricity, and most commercial systems are currently 15 to 20% efficient. In spite of these limitations, it actually would be possible to power the entire world with today's solar technology. We'd need the funding to build the infrastructure and a good deal of space. Estimates range from tens to hundreds of thousands of square miles. Which seems like a lot, but the Sahara Desert alone is over 3 million square miles in area. Meanwhile, solar cells are getting better, cheaper, and are competing with electricity from the grid. And innovations like floating solar farms may change the landscape entirely. Thought experiments aside, there's the fact that over 1 billion people don't have access to a reliable electric grid, especially in developing countries, many of which are sunny. So in places like that, solar energy is already much cheaper and safer than available alternatives like kerosene. For, say, Finland or Seattle, though, effective solar energy may still be a little way off.
You may have relaxed in a natural hot springs pool, or seen the old faithful geyser blasting hot water into the air in Yellowstone National Park. But have you ever thought of where all that heat comes from? Well, it comes from deep beneath the surface of the Earth, and it's called geothermal energy. And we can use it to generate clean, renewable electricity. Okay, here's how geothermal works. Heat from the Earth's crust warms water that has seeped into underground reservoirs. In some places, when water becomes hot enough, it can break through the Earth's surface as steam or hot water. This usually happens where the Earth's crust, or plates, meet and shift. In the past, taking advantage of geothermal energy was limited to areas where hot water flowed near the surface. But as geothermal technologies advance, we can leverage even more of these natural, renewable energy sources. Engineers have developed a few different ways to produce power from geothermal wells drilled into the ground. Have a look at this. It's a dry steam geothermal power plant, and it's the most common type of geothermal technology used today. Underground steam flows directly to a turbine to drive a generator that produces electricity. Pretty straightforward. Another geothermal technology is called a flash steam power plant. A pump pushes hot fluid into a tank at the surface, where it cools. As it cools, the fluid flashes, or quickly turns into vapor. The vapor then drives a turbine and powers a generator. A binary cycle plant works differently. It uses two types of fluid. Hot fluid from underground heats a second fluid, called a heat transfer fluid, in a giant heat exchanger. The second fluid has a much lower boiling point than the first fluid, and so it flashes into vapor at a lower temperature. When the second fluid flashes, it spins a turbine that drives a generator. The environmental benefits of this clean, round-the-clock, renewable energy source are substantial. Low emissions, small physical footprint, and minimal environmental impact. The few byproducts that can come up are often re-injected underground. Geothermal energy can also help recycle wastewater. In California, wastewater from the city of Santa Rosa is injected into the ground to generate more geothermal energy. Some plants do produce solid waste, but that solid waste may contain minerals that we can remove and sell, which lowers the cost of this energy source. The U.S. Geological Survey estimates that untapped geothermal resources in the United States, if developed, could supply the equivalent of 10% of today's energy needs and cut our dependence on fossil fuels. In fact, electricity generated by geothermal energy already provides about 60% of the power along the Northern California coast, from the Golden Gate Bridge to the Oregon state line. Geothermal energy, helping to push America toward energy independence and a clean, renewable way to meet our growing energy demands.
Tidal power. Tidal power is a form of hydropower that converts the energy from the natural rise and fall of the tides into electricity. Tides are caused by the combined effects of gravitational forces exerted by the moon, the sun, and the rotation of the earth. Tidal plants can only be installed along coastlines. Coastlines often experience 2 high tides and 2 low tides on a daily basis. The difference in water levels must be at least 5 meters high to produce electricity. Tidal electricity can be created from several technologies, the main ones being tidal barrages, tidal fences, and tidal turbines. Tidal barrages are the most efficient tidal energy sources. A tidal barrage is a dam that utilizes the potential energy generated by the change in height between high and low tides. This energy turns a turbine or compresses air, which in turn creates electricity. Tidal fences are turbines that operate like giant turnstiles, whereas tidal turbines are similar to wind turbines, only underwater. In both cases, electricity is generated when the mechanical energy of tidal currents turns turbines connected to a generator. The generator produces electricity. Ocean currents generate relatively more energy than air currents because ocean water is 832 times more dense than air and therefore applies greater force on the turbines. Tidal power is easy to install and renewable, having no direct greenhouse gas emissions and a low environmental impact. Because the ocean's tidal patterns are well understood, tidal energy is a very predictable energy source, making it highly attractive for electrical grid management. This sets it apart from other renewables that can be more unpredictable. However, adoption of tidal technologies has been slow, and so far the amount of power generated using tidal power plants is very small. This is due largely to the very specific site requirements necessary to produce tidal electricity. Additionally, tide cycles do not always match the daily consumption patterns of electricity and therefore do not provide sufficient capacity to satisfy demand. That's tidal power.
Wave energy is created by the movement of the ocean's surface. When a wave rocks a boat back and forth, it's doing work. That energy can be captured and used to generate electrical power. If harnessed properly, it has the potential to provide 10% of the world's energy needs. The 3 most common methods to harness wave energy are attenuators, overtopping systems, and point absorbers. The attenuator rig sits upon the ocean's surface, giving it a snake-like appearance. Each section is connected by a joint that allows the attenuator to undulate along each wave. The movement of the wave pushes and pulls hydraulic cylinders, causing fluids to compress into high-pressure accumulators, creating an electrical current. The attenuator was the first wave-powered generator implemented for commercial use and has the capability of powering up to 500 homes per unit. In March 2003, a European team in Denmark launched a floating 237-ton prototype utilizing an overtopping system. The overtopping works like this. When a wave approaches the rig, 2 wave reflectors guide the water to the center and up a curved ramp into the reservoir where the water is stored. From there, it's run through several hydro turbines. The water pressure spins the turbines, and the energy is converted into electricity with a magnetic generator. Overtopping rigs can withstand environmental hazards fairly well. The rig was designed to be large and heavy to combat any rolling and pitching. The low floating and heavy design allows giant winds and waves to simply pass over the rig. Another way to collect wave energy is using a point absorber. A point absorber works using a buoy that floats above the water to generate power. A giant shaft is anchored to the seafloor with the buoy secured on top. As the buoy moves up and down with the waves, the pumping action is converted into electricity. A single unit can generate enough power for 40 homes. The next generation is predicted to generate 4 times that amount. Put them together in a farm and a power plant is born. With further research and development, wave energy just might become a major contributor to the team of renewable energy all-stars.